Let's continue our discussion from last time where we started looking at anomaly detection in multiple dimensions. So let's ask ourselves the question, what are kNearest neighbors? We've talked about a few different approaches to anomaly detection so far. Really, we've been focusing on the probabilistic and statistical approaches like Benford's law, z-scores, Mahalanobis distances. The previous videos actually in this series are in the upper right hand corner if you need to review. But now we are transitioning in this series to more of the machine learning based techniques to anomaly detection, like kNearest neighbors, called KNN, local outlier factor, which is based on kNearest neighbors, isolation forests, classifier adjusted density estimation, also called CADE, and one class support vector machines. So let's start working through the right hand list. What is kNearest neighbors? Remember our goal. We're trying to discover observations that are far away or not close to the rest of the points in the dataset. Z-scores and Mahalanobis distances look at distances away from some notion of center, whether it's the mean or a more robust measure of center like the median. Well, instead of comparing a point's distance from the center, KNN looks at the average distance that point is to the closest points around it, its neighbors. See why we call it nearest neighbors? The K deals with how many of these neighbors we look at. One thing to mention, anytime you hear someone in data science mention the word distance, you need to ask the question, how do you measure distance? This isn't a straightforward question, by the way. By default, KNN is calculated with Euclidean distance. You could also use Mahalanobis distance instead. Quick tangent. Euclidean distance is basically straight line distance between 2 points. The formal equation is shown here, but let's look at the idea. Imagine you literally draw a straight line between 2 points in multidimensional space. Easy, right? But what if we change the scale of the data? Let's imagine we previously measured salary in thousands of dollars, but now we measure salary in dollars. Same data, but it's more spread out just due to the scale. Now let's look at the distance between those same 2 points. That distance looks further away if we draw our straight line between those 2 points. Well, that's not good. The data didn't change, only the scale of how I recorded the data changed. That is why when people use Euclidean distance, they will recommend standardizing your data first so that the scale of the data won't affect the calculation. Or you could just use Mahalanobis distance, the thing we talked about last time. Look at the difference in these two calculations. That piece right there in the middle is the covariance matrix, which summarizes spread in all dimensions. We are taking the inverse of that covariance matrix to account for the spread of the data in all dimensions. Okay. Tangent over. Back to the bigger story. But hopefully this helps you see why we need to think about distance measures whenever we say we're looking at the distance between 2 points. Now let's look at KNN visually. Let's go back to the same visual example we were looking at in the Mahalanobis distance video. We can see some easy outliers here visually on the lower right hand side. But how well does KNN do at detecting these? We're trying to measure distances between a point and its neighbors. Let's select this point highlighted here. Now let's look at the 5 nearest neighbors. You can pick any number for K, but I'm going to go with 5 for this example. The points that are highlighted are the closest 5 points, the 5 nearest neighbors, to the original point. The dashed lines you see are the distances between the original point and those 5 nearest neighbors. Now imagine if you looked at the average length of those 5 dashed lines. Got that average length in your head? Now let's see this for another point in the dataset. Different point highlighted here. Same idea as before though. Here are the 5 nearest neighbors of that new point. Again, I want you to imagine the average length of these dashed line distances. See how this average of distance between this point and its nearest neighbors is smaller than the previous point's average distance to its neighbors? That's because this point is located more in the center of our data cloud, closer to the other points. Now we're going to do this exact thing for every point. Here is the same graph, but each point is highlighted based on the average of the 5 nearest neighbor distances. The more saturated points have higher average KNN distances, while the less saturated and more transparent points have smaller average KNN distances. We can see the points on the outside of the data cloud, especially the 3 outliers in the lower right-hand corner, are highlighted as having higher distances. Perfect! We have some anomalies. So what are kNearest neighbors? Those are kNearest neighbors, used for anomaly detection in under 5 minutes.